All right, it's 4 o'clock, so let's get started. So welcome everyone to lecture 28, the very last one of this course. So congratulations, you have made it this far. So yeah, today we will be doing a little bit of a course wrap up, as well as continuing some of the final exam review questions that we already left off last time. Yep, and then so yeah, let's get started. So some logistical information. So the TAs, I met with the TAs earlier today. So homework 3 is now graded. So regrade requests are due in about a week. So May 1st at 11:59 p.m. Lab 4 and homework 4 are due April 26th, which means end of this week, 11:59 p.m. You're welcome, of course, to use any late day that you or your lab team might have. But you may also want to be aware that there is a final exam happening May 1st. So again, I mentioned it last class, but it's either fortunate or unfortunate, depending on how you view it, that the final exam period is May 1st to 8th, and we got assigned the first day. So yeah, maybe we can get it out of the way earlier, and then you can, I guess, go to wherever you need to be in the summer or whatever. All right, so I learned a little bit about where it is. So the location is the same room at the normal lecture. So it's over here. So hopefully the back door won't have any issues like we are having today. Based on the midterm, there should be enough space where everyone can have a free seat to the left and to the right, unless you're near the walls or whatever. So I'm hoping that there should be enough, and then there's also extra like tables and chairs if needed. All right, so we will try to grade as fast as we can and then give you feedback. So think of the midterm grade, but we're going to grade twice as fast. Part of it is because I have to leave for a major robotic conference in Japan on May 10th, so I really want to make sure I get everything done before that. So, do you have something to say? Oh, so we're going to try to give you the grade and then on GradeScope, but then you'll have maybe like, I don't know how long we can give or how long we're allowed to give regrade requests. I'll try to make sure we give them to you because sometimes there are valid regrade requests that we should look at. So the only thing that I think we ask is that you don't submit a regrade request saying, I know I wrote this, but I really meant to write this. Like, if there were a lot of those for the midterm, and I didn't give any points back for those because I can only see what I see on the exam. So I can't think, you meant to write this. So just keep that in mind. But I did give a few points back for the midterm because there were some cases when like the answer was correct, but somehow I didn't give the right score or something like that. So it does happen. And I'll have an extra office hour Thursday, which is tomorrow, from 1 to 2 in my office. So if you want to talk about any material we covered in lecture, I can do that. I can also give you advice on homework 4 to lab 4. I didn't do lab 4, so talk to the TAs for that. Then for the midterm, the final exam policies are similar to the midterm, except you can use 2 cheat sheets. So, you're welcome to bring 2 pieces of paper. Nothing else. We will give you extra papers at the end of the exam in case you need it. So, and topics to cover, the entire course, but most of it will be in the second half of class. So if you're running short on time and, you think, you don't know what to cover, then prioritize the stuff that we're going to cover prioritize the stuff that's from the review questions that I'm giving you, because there's a reason why I'm giving these review questions. Yeah. Hi. Any logistical related questions? I do have my iPad is here in case you want to type in some questions. All right. Oh yeah, so last time we left off, we finished one question, well, with one question with many different parts last time. So let's do question 2, which is also going to have many different parts today. So I think last we left off, we were talking about RL and Q learning. And so just a quick review, we were considering the Markov decision process with 3 states of A, B, and C, and 2 actions, stop and go. And you're given the following interaction sample, which are like environment steps in this table here. So the way to think about this is each row in this table is like one data tuple. It consists of, current state, what the agent took, the action, the next state, and then the reward it got at that time, at that instantaneous time step. Like not the discounted future reward, but the immediate reward. Now, I also want to mention this might come, there's a subtle point here, and that is that if you read through the samples, they're not like consecutive samples. So if the agent was interacting in some environment, this table is not what it would see from consecutive samples, because the first one goes from, I shouldn't say go, because the action is go, but the agent is in A, the action is go, it gets in B, but the next sample is from C. So if it were like consecutive, the agent would be in B, then it would continue from the prior state. But the way to think about this is, imagine that we collected a lot of interaction data, we put every single data tuple in some kind of a list or a buffer, and then we sample from it. So if you're familiar with things like training deep neural networks, it's like randomly sampling data points for training, or doing some Q learning. Like that's what's going on here. So they're not from a single episode. Just think of these as sample from a buffer of data. Right. Any questions on that technicality? That's actually a very important point here. So yeah, again, the nice thing is you can have a bunch of, like, it doesn't matter what data collection policy gave us that. If you run Q-learning enough and it visits every state action pair enough, it'll converge to a optimal policy. Like that's the whole point of, that's the whole benefit of Q-learning. All right. So maybe I'll give you a few minutes to think about these questions, like what are the Q values for the Q value of being in state C, and then you stop, as well as being in state C and you go. Maybe take a few minutes to think about that. And if you already did it from last class, like pretend you didn't do it and then try to redo it. Yeah. All right, so if we're doing Q of C and stop, then it's the first time we're doing Q learning, all the Q values start at 0. Like that's oh yeah. So all the Q values are initialized to 0. That's like an assumption where it makes everything simple. So if we have 1 minus alpha times 0, that's 0, so it doesn't matter. So we only have alpha, which is, I'm going to put it here, 0 plus Alpha is 1/2. The immediate reward is 2. And then the discount is 1. 1 times the max. So it's 1 time, the max of the Q value of the next state and then the best action, but this is going to be a max over like 0. So it's all 0 again. So this is all 0. And then you get 1. Yeah. Oh, sorry. This should be. Yeah, this should be the first data tuple. Yeah, sorry. And then what we really want is to compute C and then C and stop. So C and stop. So this is 1 minus alpha times its current Q value, which is 0. So it's 0 plus alpha is 1/2 times it's 0. Yeah, so it's 0 plus 1 times the max. The max overall possible action of whatever state happens next, which is A. And then this goes here. Now, so because we're only considering state A, we've already updated this one with a Q value of 1 from this time step. And so this whole thing is 1, and then this whole thing is 1/2. Yeah, that should be it. Yeah. So Q of C and stop is 1/2, right? Now, any questions about the Q value of state C and action stop? Yeah.
Why we need to calculate state A action stop before we calculate C stop?
Oh, why do you have to compute? Well, you mean this one? Why do you have to compute this?
I mean, why we don't need to compute A stop?
Oh, because we're running Q learning on the sample here, so you can only run it on the sample that you encounter in the data. So think of this as, you're running Q learning on some data that you've gotten. If you don't have data of being in some state and then taking an action, you can't do a computation on it. You can only update a Q value if you're in a state and you've committed to that action and then you have that data somewhere. I mean, so this is why there's a lot of study, and we'll see later about exploration policy, so that agent can be in more state action pairs. Yeah. So yeah, when we say you run Q learning on some samples, you're limited to being what's in the table. Like, yeah.
So if we assume that if there is an A stop in the table right there, and so if there's a row right there, so we need to calculate A go and A stop and comparing each other and pick the bigger one.
So if there was another data tuple like A stop, then we would compute it. But it also depends on the order that we do it, right? So if you have, I mean, if you have something like this, like A stop, B, like this is another example of a data tuple you might get. So if something like that is in the table, then we have to compute it in the Q value. Yeah. But we would only do it if it's if we sample it before this one. Yeah. So the ordering does matter, but in practice, no. When you run it infinitely often, you're gonna sample all the data points infinitely often. So you'll be able to update it based on all the data. Yeah. It's only because when we do these example questions, we usually only want to make you do like 2 or 3 computations. Otherwise, your final exam is going to be, pages and pages of something. All right, so yeah, we left off with QC of stuff, right? Now there's QC and Go. So that's the other one that I wanted to compute. So do you see why you can actually skip the computation of some of the intermediate tuples? So if you notice what's going to happen, we already covered this one, C stop A0. Now, if we do this, the third and the fourth data tuple, they're going to update the Q values over here. Like, so yeah, the third and fourth, we're going to update the numbers in here. But if you look at C go of A, then in the formula for Q learning, the next state is going to be A. So we're only going to look up the components in the table with A in them. So you can compute, these 2 rows, but it's a waste of computation because you don't need to do it. It's not wrong, you just your time is limited. Yeah. So if we know that we can skip those 2, then let's do this one quickly. All right. So it's 1 minus alpha of itself, but that's 0 again. So it's 0 half. Now the immediate reward is 2. Yeah. And the reason why there's A is because A is the next state. So you have C go A and an instantaneous reward of 2. And when you do this, the max overall possible action, you look at this, and the best one is go. So you get a reward of, or a Q value of 1. So you get a 1 here. But this is 1. And then this is 3. And then this is 3 half. Yeah. So that clear? All right. So oh yeah, all right, so what about exploration? So I mentioned that briefly earlier, like last slide you saw, here's a bunch of samples. Let's do Q learning on those. But there was a separate question of how do you get those samples in the first place? Because you have to, like, the ideal exploration policy will be a balance between how much do you have the agent just go to the states in action where it knows the most and can get the best reward based on its current knowledge of the environment, or do you try to do something new, might not be as good, but maybe sometime you'll get some really good reward, and then eventually you go there more often, and then you see, oh, it's going to give you much better reward than what the agent is currently doing. So exploration is a deep field, so we can only scratch the surface here, but we'll try to do something here. All right, so here we have another MDP. It's not connected to the last slide, even though they're still like similar terms and whatever. So if you consider just some Markov decision process that has some state A, then there are three possible actions. You go forward, you go reverse, or you stop. And the current Q values are 0.75, 0.25, and 0.5, right? Now, remember that we also talked about an epsilon greedy exploration policy. So that's probably the most common type of exploration policy, and also one that is pretty effective too. So you can do, so what it does is, you know, you, with some small probability epsilon, and epsilon is often some value like 0.1. So with some small probability epsilon, you act randomly. With a larger probability 1 minus epsilon, you act according to the current policy. Yeah, so there's a difference between the exploration policy, which is epsilon greed here. That's what the agent does when it interacts with the environment and decide, what states and what action to take to try to get, diverse data, which also, which will also give it a lot of reward. Versus, the optimal policy. So when it says current policy, that's like an optimal policy according to the current Q value. So yeah. So there's the exploration or behavioral policy, and then it's usually not the final policy that we use at test time. Why is that? Yeah, 'cause usually the final policy is just, you take the action that maximizes the Q value. Like that's what we do at test time. So based on everything that we learned from the reinforcement learning, you would just roll it out at test time with assuming the best actions according to the Q value. So yeah. So yeah, so I think, so my question to you now is, yeah, what did the, all right, so this is like these are your current Q values according to what the agent believes. And then what is the probability that we will take each action on the next move when following the epsilon greedy exploration policy? So yeah, like you have to like fill in three numbers here. So what are the probabilities? I'll give you a few minutes to think about that. Yeah. Yeah. And then, I'll also comment that, there's a common, like, you don't have to really know this in detail, but there's, like, in practice, what a lot of people do is, because if you're trying to do reinforcement learning from scratch, then you really have to try out like many different possible actions. So what some practitioners do is, when they do epsilon greedy, they actually initialize the epsilon to be 1. So it's like purely random. And then they decrease it over time, so that as time goes on, the agent just starts to act randomly less often and act according to a Q value maximizing current policy. So that's like a common technique or trick that some people do. Yeah, but here let's just assume there's a fixed epsilon for this fixed time step. So what are the probabilities? Uh, Anyone have it? Like this? Yeah. That's the rule here. So, so if you remember this from the lecture on reinforcement learning, this is like what happened if you're acting on your current policy. So whatever your current Q values think, whatever you think the Q values are, you would, if you're just trying to optimize the Q value, then you consider all possible actions that will maximize this thing. And then the argmax is just the argument, so that's the action. Hmm. Any idea? Yeah, well, yeah. So I think you got it right. So to go forward, the probability is 1 minus epsilon, and then you do plus epsilon over 3. And then reverse and stop are both epsilon over 3. See how that works? So this is this is an epsilon greedy exploration policy. This is how an agent, if it were trying to collect data, it might choose to follow that to get data samples. So with small probability epsilon, you act randomly. So because there's 3 actions, each of them equal probability because we just said act randomly, then each of them get epsilon over 3 probability. But for the action that's actually the best one, according to the estimated Q value, you actually have to add 1 minus epsilon probability to that. Yeah. So a quick sanity check, like if you sum up everything, they should sum to 1 because, this is a discrete set of probability that should be, it's got to sum to 1. Every action must be at least 0. So, does that make sense? Yeah. Yeah. So sometimes a little bit like it's a very common like bug that I've seen before. Like, some people think, you know, random action means everything other than the best action, but no, it actually means you act randomly, which could include your best current action. So, all right. So just a quick conceptual one, and then there's another computation one after this one. So this is just like a conceptual one. Like, so in a deterministic Markov decision process, like, each state action leads to a single next state. The Q-learning update with a learning rate of alpha equals 1, like that's over here. So like this is the definition of the Q-learning. The Q-learning update with a learning rate of alpha equals 1 will correctly learn the optimal Q value, assuming that all state action pairs are visited sufficiently often. So this this thing is like a common condition that people add to Q-learning to argue that, it will find the optimal policy subject to, of course, visiting enough, visiting and the state action pairs enough. And yeah, the definition of an optimal Q value is basically like this thing here. Yeah, so the Q value again is the value that the agent gets, which is the expected sum of discount and reward when it at state, ST commit to taking action A, then we'll play optimally thereafter. Just go think about that for about a minute, and then we'll discuss it. Or any questions about like about this or the explanation one or all right. So let's talk about this one pretty quickly. So I think the way to think about this is so the answer would here would be true, right? So the reason is you can try to compare the definition of what the Q-learning update does. So the way to think about alpha equals 1 is like it's gonna ignore like the current estimate of this, but it will also give you an update here. Like it will give you the update of the reward, the current reward plus the discount factor times the max overall possible action of the Q value, assuming you're at the next state and you take the value maximizing action. Now the thing is the tricky part here is I think the determinism. So normally this wouldn't, I don't think this would normally be true, but when you have deterministic MDP, then this is a transition probability. And it's the same thing as like the motion model that we covered earlier, where like the probability of the next state given the current state and the current action or current control. This thing will reduce to one term in the sum because like it's deterministic. So that's what it means here. And then basically, if you just compare this, then at some point they're going to get the same thing. The way to I think the way that I think of the, like my intuition of the Q-learning update is if you have like the 1 minus alpha here, that thing will help with, like the stability of the algorithm. So it helps with keeping the Q value like not changing too much. So if you make your alpha like closer to 0, you're going to emphasize your current estimate more. And then that means that each time step, the Q value don't change as much. So from a practical implementation view, it might make it simpler to converge. So, but if you're, if it's deterministic and you end up visiting things sufficiently often, then, you don't have to really worry about convergence if you allow it to visit the state action like essentially infinitely often if you wanted to. Yeah, so hopefully this is just an example of like some kind of conceptual question, not really a computational one, but one where you might have to think about what the definitions of these terms mean. But I think the more important thing I think is I think the important thing, you can understand this, but I think it's also very important just to know like the computation to like what we covered last few slides, like, how do you compute Q values? How do you reason about, what is an exploration policy versus the optimal policy? So. All right, so question 2D, and then there's part 1. So you thought there were only going to be 2 questions, but there's like question 2, then there's question 2D, then part 1, then there's going to be part 1.5. So consider the Markov decision process over here. So the state space consists of all squares in the grid world water park. So this is one state, this is another state, this is another state, and so on. There is a single water slide. So this is the water slide. And then there's two ladder, oh, sorry, there's two ladder squares here. And then two slide squares here. Yeah. So an agent that is in this water park can move from any square to any neighboring square. So if it's over here, it can move here or move there, right? That's what the arrow would mean. Unless the current square is a slide, in which case it must move forward one square along the slide. Yeah, so the way to think about that is, like, these arrows show the valid action. So if you're here because there's an arrow here and here, you can go either direction. But if you're over here, then the only option is to keep going right. If you're here, you could go left, like maybe you were gonna go on the water slide, but you got scared, so now you're gonna go back. So this is like the top of the ladder. You can go left or you can take the slide, in which case the next action must be to go right, and then the next one must be to go right again. Yeah. Oh yeah, the actions are denoted by the arrows between the squares on the map, and all are deterministic actions. And the agent cannot stand still. So you have to pick something to do. Yeah. All right, so the rewards are shown. So the agent feels great pleasure as it slides down the water slide. So you get +2. You get +2 here and +2 here for the next time step. A certain amount of discomfort as they climb the rung of the ladder. So you're here. If you're over here, then you go here, you get a -1. Then you go here, you get a -1. Then here you get a +2. Yeah, maybe it's like your discomfort when you climb the ladder, like if you're afraid of height. I'm not sure. Yeah, the time horizon is infinite. The Markov decision process goes on forever. All right, so any questions about the setup here, like the Markov decision process? Most questions on the final, they're not going to be this long. I just want to, in case you don't like reading long pieces of text, or maybe not. I don't know. Any question? I don't. If there's no question, then the first question is, if your discount factor is 1, and what are the optimal values of state A and state E, assuming that there are the 3 steps left. So remember that whenever we talk about value, then B, then choose the subscript is like how many steps are left. By default, if there is no subscript, just think of it as like infinite left. So the subscript is there just to tell you if if the time horizon is finite. Yeah. Otherwise, you should assume it's infinite. All right. So what's the answer for the first one? Um, Anyone want to say something? Say a number? Yeah.
I guess for like A, maybe just 0.
Why do you think?
It seems like Oh, maybe, yeah, because, you would want to approach it from the side that has, all zeros and not from the side that has negative one. Or wait, yeah, it's all zeros to approach it.
Yeah, so if there's 3 time steps left, then what can we do? We can go 1, 2, 3, 1, 2, 3. We could go like 1, 2, 3. Any of those get 0. Now you can go up here like 1, 2, 3, but you get a -1. So you wouldn't do that. If you only have 3 time steps left, you should not do that. Because it's like you get -1 versus 0. So 0 is better. What about E? It's like a 2-part question. So there's the value of E with the optimal value of being in state E with 3 time steps left. What, 4? Are you sure? Are you absolutely sure? All right, so yeah, it's 0 and 4, right? Because what happens here? You go, everything okay? Yeah. So if you're in state E, you can go either left or right, but we'll choose to go right. You get a +2 reward. Then you're here, you have to go right again. So you get +2, and then you get 4. Then with only because you can't go left. After that, though, it's a 4, right? Any questions about that one? So if there's no questions about that one, then maybe think about the second question. So again, your discount factor is 1, but what are B10 or B star? Do you say the subscript or the superscript first in that case? I'm not sure, like B star 10A, and then what are B star 10E? So you have 10 time steps left. What's the optimal value you could get? Anyone? Yeah.
So for A, it will be 2, for B is 4.
So 2 and 4. Yeah. Yeah, so what explains the difference between A and the 2 cases? So you have this as 2 now. Why?
Because we have 10 concepts right now. The A can go 50 and slide down to the letter, I mean the water slide. So it can get +2, and also have a -2 for.
Before that, -2 is before that. So with 10 time steps left, you have, all right, this is 1 time, like the way I think about it. You have 1 time step, 2 time steps, 3 time steps rewarded -1. 4 time step rewarded -2, the cumulative reward. Then 5 time step, you get the cumulative reward of 0. With 6 time step, cumulative reward of 2. 7, 8, 9, 10. Then the best we can do is just walk around with all zeros, because you can't go left here because you're forced to go right from the slide. And there's not enough time step to go back and wrap around. All right. If your discount factor is 0.1, then what are these two now? Your discount factor is 0.1. Yeah, well,
Use zero, for the first one. Because you don't wanna go up. So you just kind of stay between the zeros.
okay. What about the second one?
Start at E, you just go right, you get 2 and then 0.2, so it's like 2.3 total.
All right, so answer is 0 and 2.2. Yeah, so if I think reasoning about E is pretty straightforward. So if you're in E and you have 10 time steps left, then you can go left or right, but right is going to give you 2 rewards. So you might as well get that right away. And then you go right again, you get 2 rewards, but the discount is 0.1. So you have to multiply it by 0.1 to get 0.2. And then you get 2.2. And then you can try to keep going around, but no, with only 8 time steps left, you're not going to get any more chances for any reward. And again, you can't go left from here. Like if you're here, you have to go right. So now for A, so it's the easier way to think about this is there's like you can either like just go left and right back and forth, just get 0 reward. Or you could try going up and then right. Now, here's the way to think about this. If the agent is over here and it could go right, it can get -1. Then it goes right, it could get +2, but the +2 is discounted by a lot. So this would give you -1 plus 0.2, which is actually negative. So it makes no sense to actually even try the -1, -1, and 2 because you compare 0 versus -1 plus. And this is a negative number, so 0 is better. Yeah.
I'm just curious about how we should deal with this topic. So when we get with the first concept, should we just get the discount to the power of 1 or 0?
Power of 0. So the first time step is gamma 0, which is 1, because it's the raised to the 0 power. So yeah, this is really -1 times 0.1 to the 0 power. And then this is just 1. So yeah.
So, the discount will only affect at the second time step.
It'll affect more than the second time. The second, third, it's infinite. And yeah. All right, so we finished question 2D1, and then there's 2D2. All right, continuing from this, if your discount is 1, then what are the Q values with 1 and 10 time step left? What are the optimal Q values of being at state E and going left? Okay, so you're in state E, you have committed to taking action left, so you go left, and then from thereafter you play optimal. That's what play optimally is indicated with that asterisk. And then the subscript is how many time steps you have left. All right.
So is it 1 time step after that? Or is it just that?
All right, so if Yeah, so what this means is you only, with one time step, that means you only have one action. So that includes the most immediate action that you might take. So it would include going left. Yeah, so going left is included as part of that one. So yeah, so in this case, you go left and then you stop, basically. Yeah. All right. Anyone? All right. Anyone? How about someone who hasn't said something? What do you think? How? Well, there's two things to say. Yeah. So 0 and 3. So you got it? So with one time step left, you're at state E, you have committed to taking action left. So you take that, you get instantaneous reward of 0, and then you're done. There's no more things you can do left. So you got 0. Now, if you have Q10, that means you have 10 time steps left. Then from here, you've already committed to taking action left. So you get 0. And then you have 9 steps left. So with 9 steps left, what you would do is you would go right, right, right. And then you get +3 cumulative. Because the discount is 1, so you can just add the bump. And then after you go here, there's not enough time steps left to go back and get more rewards. So yeah. All right, next one. If your discount is 1, then what are the values? So there's nothing in the subscript. That means it's like you have as many time steps as you need. So there's no limit in terms of, you're going to be done after this number of steps. Hmm. Right? Anyone? Yeah. Yeah, very good. They're both infinity. So your discount factor is 1. So you can take the time horizon is infinite. So if you're over here, you might as well just keep going right, like keep going clockwise around the whole thing. You get -2, but you get +4, so you get a net +2 every time you go around. And then because there's no limit, you just get an infinite sequence of +2, +2, +2, +2, and so on. Yep. All right, what about this one? Same thing as above, but your discount factor is now 0.1. Yeah,
For A is 0. And for E, it may probably converge to a number slightly smaller than 2.2, but I'm just looking.
you can give me an exact number?
2.2.
All right, very good. So it's 0 and 2.2. So because the discount factor is 0.1 now, then it does not make any sense to go through this entire sequence because you get -1, you get -1 discounted, but then you get +2, but it's discounted so much that it's like it's the same thing that we covered here, right? So you can try to do a single -1 and then you think a +2 is gonna help. But if the discount is 0.1, then it's better not to even do that because you get that the whole thing's gonna be negative. And so if you're here, just best to like, dither around here. For E, it's best to go once to get the positive reward, and then just go back and forth and get 0 reward. So it doesn't converge, it's exactly 2.2. Yeah. But any questions about that? Like I don't have any more 2D 2E or whatever. I think we're done after this. With this topic. So I think to recap, like my suggestion is just maybe try to be familiar with like this example, like how to interpret like what the V's and Q's mean, how to sum up everything, and remember the exploration policy, and then the difference between like Q learning exploration policy versus the optimal policy. Think of these as like your optimal policy. Yeah. I mean, these are optimal values, but you can derive your optimal policy by, you take an argmax over the action. This, I guess, should be, yeah. It doesn't really matter if you have the only reason to have the asterisk is to indicate that it's optimal. Yeah. All right, last practice question, and then we'll do some like concluding overview stuff. So last question on forward Euler. So you remember that from before? In the lecture about the simulation and dynamics, I mentioned that, the way that robot simulators work is you have a bunch of differential equations, but you've got to discretize it to be on a computer. And so there's a small time step where you have to simulate things. And you can do that with you could do that with a forward Euler. It's not recommended because forward Euler is very bad, but it's important to know how it works. So this equation is from the lecture, like I just copied it from the lecture, and then yeah, if you consider the differential equation y dot equals alpha times y with initial condition, like this. So you could, if you wanted to, you could solve it in closed form, but we're going to pretend that we want to simulate it instead. So the simulation, if it's good enough, is going to be the same as the closed form. In practice, there's always going to be noise because you discretize it, but then you simulate it using the forward Euler method for 3 iterations. And then, yeah, you compute the y1, y2, and y3 using forward Euler, assuming that the step size is 1. So the step size is h here. Yeah. Hmm. I, anyone? Oh. I'm vaguely trying to point at someone, but yeah, maybe, I don't know who I'm pointing to. I, did you get it? Oh, you still need another minute? Yeah,
Y1 is 1 plus alpha. Y2, 1 plus 2 alpha plus alpha squared is Y3. 1 plus 3 alpha plus 3 alpha squared plus.
so. So yeah, if y1 is 1 plus alpha, y2 is 1 plus alpha squared, the whole thing squared. And then y3 is the whole thing 1 plus alpha to the third power. In general, this is a particular pattern from this differential equation. It's not generally true. Like most equations are not going to be like that. But it's just something that it happens to be true from this particular choice of a differential equation. And if you think about it, if you think about what's happening here. So you can think about this as, if, yeah, if alpha is 1, then the first one would be like 2. And you can, another way to think about this is like, you can think of the subscript as being like an x coordinate, and then at the beginning, you might get 1 here, and then you get, for y1, you get, this is, I guess it's 1 and then y1. This is 2. And then this is 4. And then this is 8. So it goes like this, and this is the pattern of the exponential function. So what will happen is the real exponential function looks like that. And then the forward Euler is going to try to simulate that by discretizing time, and then you go from one time step to another and try to match the real function. Obviously, the shorter your step size, like if your step size is much smaller than 1, then the approximation will be better, but it'll be slower. So. Yeah, so I think this is a good time to take a 5-minute break, and then we'll wrap up the course soon. So yeah, I'll see you at 5:10. call your question?
Yeah, that's the question.
Let me turn off my video.
Oh, sure.
Um, We all go back at the exact same time. You're like synchronizing something. Right. Well, anyway, I want to let me bring up a point that a question that I got. So just to clarify a lot of the terms. So when so just a notational thing. Whenever we have Q1 or V1, just think of that as this is some value, assuming the agent only had one action left that it can take. This one here does not mean, it does not have any connection with go through each of these samples one. That's a different, completely different thing. So the reason is you can go through the table infinitely often and then keep running Q-learning updates. Then you can still later say, well, okay, let's imagine we only have one time step left, and then compute the value from it. But it's like, yeah, so this one, or if this were like two or three, it does not have any connection with how long you run Q-learning. It only says what's the maximum number of time steps left that we can interact with the Markov decision process. Yeah. Now, when we talk about Q-learning, if I give you a table of transition, which are state, action, next state, and the reward, if I give you this table and say run Q-learning on it, then that will mean you'll run through it run through each sample once, starting from, the top and then go to the bottom. So you would do like one iteration of Q learning would be like 6 updates, basically. If I tell you run Q learning infinitely long, then you would constantly go back and forth across these samples and constantly update them. You might have to do that in some cases. You have to do that to make the value. No, the value might be changing a lot. In practice, if you're discounted one, they usually don't change too much. Yeah, but also I also want to mention this table here is not the same as a transition probability definition. That's completely different too. What all this is saying is we saw that the agent exploration policy said it was in some state A, it took some action go, it landed in B and got reward of 2. But it said nothing about what is the probability of state B being the next state conditioned on the agent being in state A and taking action go. So this is the transition probability definition, right? So if we know this, that's like knowing the transition probability definition. This is not the same as that. These are samples. But if you sample this infinitely often, you'll see that the numbers converge to something like that. Like if it says the probability of being in like if it says so if if I gave you the definition of the transition probability of your next state being B, given the current state is A, the action is go. If I told you that's 0.5, then you would expect to see that whenever you see A and go, B is going to happen 50% of the time. So your sample should reflect that. Yeah. So again, this is the difference between the sample and then the definition here. That's the key distinction. Yeah. So yeah. So keep that in mind. The difference between sample and then the transition definition, and then also the running an iteration of Q learning versus the numbers here, which are a number of time steps left and an interaction like for the agent to take. Yeah. Yep. All right. Any other questions? I can try to give you some more practice problem with it if you want. Yeah, let me know on Piazza or whatever. Hi, let's move that over here. So, well, again, this is the last lecture. Again, if you're wondering what that is, that's from the course website. I think most of you know where that is because most of you probably look at the recording based on the attendance in the class. So, or you can find them on my personal YouTube channel. You can see all the other videos I posted there too. Comments are disabled though. I've had too many comments are like nasty or whatever, so no comments on the video. Yeah, but anyway, we covered a lot in this course, right? So we covered a lot of the math fundamentals. So the reason why we covered linear algebra, optimization, and probability is because those are very important for robotics. So like you need to know linear algebra to understand, like, a lot of times we have systems of equations that you saw, then we have to do some, operations on it. I mean, probability, we saw an example here, like there was, the entire world, you can model it with, probability, like what's the probability that the robot is going to be in this state, given it takes this action and in a current state. So like these are, I would say, the most important math area to be familiar with if you're doing a lot of robotics work. I would say if you're doing robotics research, so if you're doing research, it's probably more important to know the math stuff. In industry, it might be less important, if only because in industry, a lot of time robots are put in situation where there's complete certainty about the environment. So like in research, we often try to make it unstructured, so we have to read even more about probability. But even though, probability is so important that it's good to have intuition on it. So yeah, so we talked about like Bayes filters. So Bayes filters are, I would say they're broadly an AI term. They're closely related to reasoning about probability, because you have to reason about like, the combination of different variables, then conditional independence assumption, and then you can define conditional probabilities from that. We talked about a lot of fundamental robotics problems. So a lot of the first half of the course was on the state estimation stuff. So you remember all those equations that were there, like deriving the Bayes filter, the common filter, particle filter. Don't forget those. So, and then yeah, we talked more about state estimation, but we also talked about, oh, this should be localization. Sorry, localization, and then there's mapping. So maybe that was an autocomplete by the PowerPoint or whatever. Yeah. And then we also talked more about, these are fundamental problems in robotics, but knowing like configuration spaces is probably even more fundamental, because you have to describe robots that way. So this is like the language that we use to say, where is the robot? And then I think in the second half, we talked more about robotics fundamentals. So we talked about transformation. So, those are translation and rotation, because very often robots are made of rigid links, and then you have to reason about what's the relationship between one link and the other, and what is the transformation to apply to go from one joint to another, as well as reason about what is the transformation from like a camera to some object, or to camera to the robot base. So you can reason about, if you have an image, and then what's the pose that the robot should go to grasp that object. Yeah, we talked about things like kinematics, and which is also related to like simulation, like how you describe the motion of the robot, and as well as dynamics here. Oh yeah, then there's also the forward and inverse kinematics. So like forward kinematics is given the joint angle where the pose of the end effector, then inverse kinematic is you have a desired end effector pose, what are the joint angles to get to that? And you can extend that to like multiple end effectors and more complex robot. Yeah. And yeah, we talked about rotation and 3D representation. So remember the lecture, I was very self-promoting, like saying, look at my paper and blog post, like that was this one. So you have to know rotation to deal with robotics. Like you have to know like Euler angle and why they're bad, and then axis angle, why they're bad, and then quaternion, why they're good, and rotation matrices, which are good and bad. Yeah. And then there is the fundamental problem of motion planning. So yeah, we talked about sampling-based motion planning. There's another set of motion planning algorithm called optimization-based. We mostly didn't talk about that, mostly sampling-based one. And then there's AI fundamentals. I got the reason is a lot of robotics uses AI right now. So there's a lot of interest in trying to get robots that can operate autonomously in today's world, especially because we have a lot of data, and data is often the fuel that we need in order to train the method using like learning-based methods like reinforcement learning and imitation learning, which make use of the Markov decision process framework that, we were talking a lot about example Markov decision processes here. And I would say modern stuff, the main reason is, sim to real, like training something in sim and then directly deploying it in real, like that's something that's gotten very popular very recently because of how good many of the simulators have gotten. Oh yeah, we covered a lot of topics. So Any comments? So I think if I had to think about, the current and the future of robotics, a lot of common themes today relate to stuff like multimodality. So many robots are not just taking in visual information, but there's also tactile information and language information. Or tactile and language are the most common ones to pair with vision, along with there's a lot of interest in autonomous robots. So you can be a robotics researcher, then focus on, here's the hardware design, which, we need advances in hardware, but many people in robotics are interested in autonomous robots that can do many interesting and important tasks. Yeah, there's a lot of interest in multi-agent. So like, you can also argue, like, as we're gonna see here, this is Eric from TRI. Like, I met him a couple of times, and he's got a bunch of teleoperation control, and then there's like multiple robots that are working together for some bimanual manipulation. Then there's generative AI, which I don't think you need an introduction to that. You probably would ChatGPT for, like, homework help or whatever. Not the final exam though. And so I like this video because this video is from Toyota Research Institute, which is one of the leaders in doing robotics research. And they have this video by, I think, Russ Tedrick, who is a leader in robotics. Like, I cite one of his textbooks and with the dynamic stuff. Like, if you remember that cart pull and the inverted pendulum, like, he's the guy who wrote that online textbook, which you can access, and then has a bunch of free lecture videos on his YouTube channel, which is one reason why I wanted to record it so I could have a lot of courses online like he did. How do I?
Here at TRI,
I can't get the subtitle to be on. All right. So I click on the setting and then it just disappears. So I can't make the. All right, the subtitle. I'm just gonna let the video play. You can look at the subtitles on YouTube, or I'm not fluent in Japanese, but I can't. I don't know what it means. So
robots should amplify people at home and at work. To achieve this, we conduct cutting-edge research to make robots more flexible, robust, and general purpose. We've had a bit of a breakthrough. Today, TRI is announcing a new method to teach robots dexterous skills quickly and easily. Our approach is built on a powerful generative AI technique called diffusion policy. This allows us to teach robots much faster and with significantly fewer demonstrations. The approach holds great promise for creating what we call large behavior models. Just like large language models have revolutionized chatbots, these behavior models will allow robots to perform useful work in ways never possible before.
Up until now, the majority of robotic manipulation work has focused on pick-and-place style tasks, where a robot is limited to relatively simple sets of objects it's rearranging. Our new approach goes significantly beyond that and lets us explore much closer to the limits of the hardware. TRI's robots are now capable of using tools, pouring liquids, and peeling vegetables. It's exciting to see them engaging with their environments in rich, multifaceted ways, and all achieved without changing any code or explicitly programming any new skills. Using this technique, we've taught over 60 diverse behaviors to our fleet of robots. The process starts with a teacher demonstrating a small set of skills through teleoperation. Then, our AI-based diffusion policy learns in the background over a matter of hours. It's common for us to teach a robot in the afternoon, let it learn overnight, and then come in the next morning to a working new behavior. To make this level of dexterity possible, every part of the robot platform must be solid, from the hardware all the way up through the entire software stack. One key enabler is providing human teachers with a sense of touch or a haptic teleop device. Also, just like people, we found that robots learn better when they have a sense of touch. And a perfect example of this is the task of flipping a pancake, where the robot has to make contact with a surface it can't see. Without a sense of touch, it struggles and performs poorly, but is successful in learning the skill once it's able to feel its interaction with the environment.
This is only the beginning. Our team is deeply focused on achieving large behavior models that I mentioned earlier. We anticipate the next breakthrough will be when we train the robots with enough dexterous skills that they're able to generalize, performing a new skill that they've never been taught. To realize this, we're building a diverse curriculum for robot learning, essentially a kindergarten for robots, to teach them numerous foundational skills that are useful for working alongside people. We're on pace to teach hundreds of new behaviors by the end of the year and over 1,000 by the end of 2024. We're also leveraging our expertise in simulation to augment our real-world teaching. And finally, we're developing fundamental tools for fleet learning so that when one robot learns, they all learn. I've been working in robotics research for a long time now. The tasks that I'm watching these robots perform are simply amazing. Even a year ago, I would not have predicted we were this close to this level of dexterity. And the rate at which we're able to teach new skills is simply astounding. Nearly every day, I wake up to a new message showing the robot doing something it couldn't do the day before. This is an incredible time to be a roboticist.
So I do think 2024 is going to be a big year for robotics, and then you can see a summary from Jim here about, and you can find it on his LinkedIn page. Like for some reason he's super active on social media, so you might have to scroll through a lot, but this is from 4 months ago. And so I think he said, he thinks it's like 3 years away from the ChatGPT moment for physical AI agents. And we've been cursed by Moravec's paradox for too long, which is the phenomenon where tasks that humans find easy are very hard for AI and vice versa. Like AI playing Go is very good, but humans find that hard. Humans find things like folding laundry easy, but that's hard for robots. So stuff like that. And then gives a sense of like what 2023 was like, and he talked about simulation. And Isaac, like Isaac, although he is employed by NVIDIA, so take that with a grain of salt. My view is like, I think 2024 will also be a big year for robotics. Like from my view, I would like to, I want to do a lot in this field, so that's why my lab's focus is a lot on dexterous manipulation of very complicated tasks. The one thing is, at least from a research view, maybe it's different in industry, but for research, it's very important to be clear about the failure cases and limitations. So one thing that you'll learn if you do like robotics research is that robotics is very difficult, and it's very important that we be upfront about like the limitations, failure cases, and the general public, I feel like, can get misled very easily with cherry-picked video. So you show a robot doing something, but then it turns out the people who made the video had to run it 100 times to get one success. So that's not really what I would call a good robotics thing. But yeah, I think this will be it's a very exciting time, and hopefully you got a good sense of what it's like to be doing robotics, and then I hope you got a good foundation of robotics in this course. So that's all I have for today. So I think we will see you next most of you next week for the final exam. And there's also like a student evaluation. Like you can fill out the learning experience. So I think there's a link you can type in or like give your feedback on the course. And then I encourage you to do that. Do it first and then talk with others about it. And I'll see you later then. All right.